I'll explain the larspathgram function. It's a scikit-learn function used within the least angle regression (LARS) framework. It cleverly uses the gram matrix and a vector derived from the data and target variable, explained below, to efficiently compute the regression coefficients. This avoids directly working with potentially large datasets. The gram matrix is super important. It's the result of multiplying the transpose of the design matrix, X, which is just your data matrix flipped, by itself. Think of it as a summary of the relationships between your predictors. It's key for efficient calculations in LARS. The formula X at X represents matrix multiplication of X transpose with X. The regularization path is what larspathgram gives you as output. It's a sequence showing how your regression coefficients change as you adjust the strength of regularization, controlled by a parameter called lambda. Imagine it as a graph showing how your model's parameter estimates evolve. This is another key input for larspathgram. It's the matrix product of the transpose of the design matrix, X, and the target variable vector, Y. It essentially summarizes how your predictors relate to your target. The formula X at Y represents matrix multiplication. Least angle regression is a method for fitting linear models. The larspathgram function is a specific, efficient way to implement it, making use of the gram matrix to speed things up, especially for large datasets. This is a multiple-choice question testing your understanding of the larspathgram function. You will need to assess the accuracy of several statements concerning its properties, function, and advantages. I'm looking at the least angle regression, LARS, algorithm, specifically how scikit-learn implements it using the function larspathgram. LARS is a clever algorithm that iteratively builds a linear model by adding predictors one at a time, based on how well they correlate with the remaining errors. The larspathgram function uses a special matrix, the gram matrix, to make this process more efficient. This function uses this matrix to get the regression coefficients without directly calculating correlations at each step. This question tests your understanding of larspathgram and its properties. We'll examine 4 statements and determine if they are true or false. Get ready to test your knowledge. This statement is absolutely correct. The gram matrix, which is obtained by multiplying the transpose of the data matrix, X, by the data matrix, X, must be positive semi-definite. This is a crucial mathematical requirement for the algorithm's numerical stability. If it's not, the calculations can become unstable and unreliable. Absolutely. This is true, especially when you have a large dataset. The larspathgram function uses the gram matrix, and working with this smaller matrix is way faster and more memory efficient than working directly with the original, potentially huge data matrix X. It's a big computational advantage. Yes, the regularization path is the main output of larspathgram. This path shows how the regression coefficients change as the regularization parameter, lambda, changes. This allows you to see the trade-off between model complexity and how well it fits the data. It's super helpful for model selection. I see the gram matrix, X, as a super efficient way to represent the relationships between my predictor variables. It's like a summary of all the pairwise relationships within my data. Calculating it directly reduces the number of computations needed, especially when I have a lot of variables. Think of it as calculating the similarities of all the features in one go. This function is a smart implementation of the least angle regression algorithm. It cleverly uses the gram matrix to speed things up. Instead of working directly with the large data matrix, it leverages the gram matrix to calculate coefficients at different levels of regularization. I see the regularization path as a sequence of coefficient values. Each coefficient value is associated with a different value of the regularization parameter, lambda. It's like a movie showing how the model's coefficients adjust as we add more penalty to complexity. This helps choose the optimal balance between model fit and simplicity. Least angle regression, LARS, is a clever algorithm to find the best linear model for your data. It adds variables step by step, focusing on those most correlated with the remaining unexplained data. The *lars_path_gram_ function uses this approach, but rather than working directly with your data, it uses the gram matrix, XX, as a shortcut. This makes it particularly efficient for large datasets. This represents the matrix product of the transpose of your data matrix X with your response variable Y. In simpler terms, I see it as another crucial intermediate calculation used by *lars_path_gram_ for efficiency. It summarizes the relationship between each predictor variable and the target variable, streamlining the Lars algorithm. I see you're interested in least angle regression, or LARS, and specifically its implementation using the larspathgram function in scikit-learn. LARS is a clever algorithm for building linear regression models. It adds predictor variables one by one, choosing at each step the variable most correlated with the current residuals. larspathgram uses a clever shortcut that significantly speeds up this process. This question focuses on understanding the advantages and requirements of larspathgram, which is a more efficient way to run LARS. You'll need to know what a gram matrix is and how it impacts computation. The gram matrix, which is X transpose multiplied by X, XX, needs to be positive semi-definite for larspathgram to work correctly. This means that all its eigenvalues must be non-negative. This condition is vital for numerical stability and to avoid errors during the algorithm's calculations. I can tell you that larspathgram is much faster, especially when the data matrix X is huge or sparse. The reason is that larspathgram operates on the gram matrix, which is smaller than X, resulting in fewer computations. Think of it like this: instead of directly working with a massive dataset, you summarize it into a smaller, more manageable representation, the gram matrix. The beautiful thing about larspathgram is that it gives you the regularization path, which shows how your regression coefficients change as you vary the regularization parameter, lambda. Understanding this path is key to finding the optimal balance between model complexity and predictive power. The gram matrix is a shortcut. It's the result of multiplying the transpose of your data matrix, X, by itself, X. This compact matrix contains all the pairwise inner products of the columns in X, which is important information for LARS. By using it, larspathgram avoids unnecessary computations. This is another clever shortcut. This term represents the product of the transpose of your data matrix, X, and your response vector, Y. This matrix contains information about the relationship between your predictor variables and the outcome you are trying to predict. These are the values that tell you how each of your predictor variables influences your outcome variable in your model. larspathgram gives you these coefficients, showing how they change as you adjust the regularization parameter lambda. This question asks you to identify the correct statements about scikit-learn's *lars_path_gram_ function, used in least angle regression. We'll look at each statement to figure out which ones are true. Let's dive in. I found this statement to be false. Although *lars_path_gram_ is efficient, it still implicitly uses the correlation information between residuals and predictors through the gram matrix and XY. It doesn't completely bypass this crucial LARS step. This statement is true. A positive semi-definite gram matrix, X. T at X, that's the transpose of X multiplied by X, is a must for the algorithm's stability and reliability. Without it, you'll run into numerical problems. I say true. Using the gram matrix offers a significant computational advantage, particularly when dealing with large or sparse X matrices. It dramatically reduces the number of calculations needed. This is true. The main purpose of *lars_path_gram_ is to give you the regularization path, showing how the regression coefficients change as the regularization parameter, lambda, changes. It's a key part of understanding how the model behaves under different levels of regularization. The *lars_path_gram_ function takes two inputs: the gram matrix, X. T at X, which is the transpose of the design matrix X multiplied by X, and XY, X. T at Y, which is the transpose of X multiplied by the response vector Y. These are crucial for efficient calculation within the Lars algorithm. The function's output is the regularization path, a sequence of coefficient values for various values of the regularization parameter lambda. This path helps you understand how coefficient values change as you adjust the regularization strength. I say this statement is true because the gram matrix, which is X transpose multiplied by X, must be positive semi-definite. Otherwise, the algorithm can become unstable and give unreliable results. Think of it like building a house. You need a solid foundation. A positive semi-definite gram matrix provides that stable foundation for the least angle regression algorithm to work correctly. This one's true, too, when dealing with massive datasets, using the gram matrix, that's X transpose times X, is a major computational shortcut. It's like finding a clever path instead of trudging through a whole forest. It directly reduces the number of calculations needed, especially when X is large and has many zero entries, sparse. Absolutely true. The whole point of Lars_path_gram is to give you the regularization path, a series of coefficient values for different penalty strengths, lambda. It's like watching a movie in slow motion. You get a clear picture of how each coefficient changes as you adjust the regularization parameter. This is extremely valuable for model tuning and interpretation. I'd say false here. While Lars_path_gram is efficient, it doesn't completely avoid calculating correlations. It uses the gram matrix and XY, X transpose times Y, to implicitly handle those correlations, but they are still fundamentally involved in the calculations. I analyze the scikit-learn function, larspathgram, which is used in least angle regression. I'll be focusing on how it uses the gram matrix and what makes it efficient. The gram matrix is simply the result of multiplying the transpose of a matrix X by itself. Think of X as your data, xt is its mirror image. Their multiplication gives us a summary of how the different data points relate to one another. This function is a smart way to do least angle regression using the gram matrix. This makes computations quicker, especially when dealing with huge datasets. This is a fancy term for a graph that shows how the predictions change as we adjust the strength of our regularization, which helps us find that sweet spot of fitting the data well without overfitting. This is the main question, which tests your understanding of the larspathgram function and how it works. I explain why the gram matrix must be positive semi-definite. The gram matrix needs to be positive semi-definite for the larspathgram algorithm to work correctly. If it's not, the results could be unstable. This condition ensures the matrix is mathematically well behaved during calculations. I explain why using the gram matrix is more efficient. When working with a massive dataset, using the gram matrix is much faster than using the original data directly. It's like having a summary that's easier to work with. I explain what the regularization path is and why it is important. The output of larspathgram shows the adjustment to predictions as we change the regularization parameter. This helps us find the best balance between the model's simplicity and accuracy.